All right, so let's continue on with another example. Say we have y double prime minus 2y prime minus 3y equal to, let's try sine of x. Let's try to solve this. Now remember, what was our approach to such questions? First, we find just one solution. We just make a good guess and find just one solution. Then once we find that one solution, we also solve the homogeneous equation, set the right side equal to 0. We find the general solution. And if I say yp is the one solution to this one, p is for particulars, meaning that there's just one particular solution to this equation. And we take the complementary solution. Complementary solutions are the equation where you set this side equal to 0. Find the solution. We know how to do that, right? And we add them together. That gives you the general solution. So that's how you find the general solution. Sometimes you write G under it. So the general solution to this differential equation is you find one particular solution, you add to it a complementary solution. That's how you get it. Okay? All right. So let's play the same game. I want sine x on the right side. What should I plug in for y? What kind of functions differentiate to sine?
Cosine.
Cosine, good. Do you, so let's try that. So let's try, it's basically trial and error. Remember, we're not solving, we're making guesses, good educated guesses. So let's try with y equals to cosine of x. Y prime is negative sine x. Y double prime is negative cosine x. Now plugging all of them to the left side, let's see what we get. We get negative cosine x plus 2 sine x, and then minus 3 cosine x, so that you get negative 4 cosine x plus 2 sine x. Of course, it was just shot in the dark, so of course this didn't match the right side. So is this a solution or not? Y equal to cosine x. It's not a solution yet. Okay? However, we see some good side and we see something good and bad at the same time. We see the sine x as we want it. Okay, this is good. We want sine x. But we also have this cosine x that we don't want. So we somehow need to figure out a way to get rid of the cosine. How should we do that? How can we get rid of the cosine?
Add 4 cosine? Add 4 cosine?
I mean, if you add 4 cosine to y itself, there will be 5 cosine, and the end result will be just 5 times this thing. So just having more cosines would just give you more products of this, this times some constant. So it's not going to help us. Yeah? Any other ideas? Say it loud. What do you want to do?
I know, maybe make y like cosine plus sine.
Yeah,
And hope it cancels
that's
out.
exactly what you want to do. Yeah. You want to try. If this failed, then you want to try another one where you do cosine plus sine. Both of them. Maybe that's going to work. Who knows? So I differentiate. I get cosine x, and differentiating one more time, I get negative sine. Now let's plug all of these into this left side and see what we get. Just make this larger. The first, y double prime is negative cosine x minus sine x. minus twice y prime is negative sine x plus cosine x. And then minus 3 times cosine x plus sine x. This here. Okay, now look at what we have. Some of them have cosines, some of them have sines. So let's gather the like terms. First for the cosines, what do we get? Negative cosine minus 2, so that's negative 3 cosine minus 3, so we have negative 6 cosine. And then negative sine plus 2, positive 1 minus 2 sine x. Okay. So again, is it success, fail? Which one? Fail. It still doesn't match the sign. However, we learned something on the way. It looks like if we have some cosine and sines together, they both create cosine and sines. So maybe with just the right amount of mixture of cosines and sines, somehow maybe we can make this work out so that cosines just delete each other, just cancel each other away, where the sine x will be the sole survivor. So that's the final thought here. So we just want to figure out the right mix of cosine and sine. So how do we do that? How do we generalize that thought? Those strange things. Okay, I'm still waiting. What should we do?
Make it negative cosine?
Yeah, what should it be?
Put a variable.
You wanna?
Put a variable, right. I mean, of course, we can do this all day. Just put 1 and 2, 2 and 1, negative 3 plus 5. But that's going to take too long. The better way is to just rewrite this as something times cosine or something times sine. A times cosine x plus b times sine x. Just do that. And then you differentiate and plug into the left side, and maybe we can make this work. Y prime. So this is negative a sine x plus b cosine x. Y double prime, negative a cosine x minus b sine x. And therefore, when you calculate y double prime minus 2y prime minus 3y, and you plug in all these individual calculations we've done, negative a cosine x minus b sine x minus 2 times negative a sine x plus b cosine x, then minus 3 times a cosine x plus b sine x. Now let's gather all the cosines together and sines together, because our goal is to get rid of the cosine while making the sine become 1. Okay? Sine's coefficient become 1. All right, negative a minus 2b minus 3a. So negative a minus 2b minus 3a. Cosine x. And then for the sines, negative b plus 2a minus 3b sine x. Okay. Right. What do we want again? This one should be equal to 0. And you want this to be equal to 1. So that it will match the right side, which is just sine x only. Okay, that's why you want this to be 1 and this to be 0. Let's solve. It's somewhat surprising that you can actually solve it, because you have two equations and two unknowns a and b. You can solve it, right? So you have negative 4a minus 2b should equal to 0, whereas 2a minus 4b should equal to 1. Okay. If you solve this for b, you get b equals to negative 2a, right? If you move this to the other side and divide by 2, you get b equals negative 2a. Plug it in here, you get 2a plus 8a equal to 1, which gives you a as 1/10. And then plugging it back to b, you get b equals to negative 2 times 1/10, which is negative 1/5. I solved the system rather quickly, but you will see that the answers make sense. Okay? All right, so we know that if our choice was 1/10 cosine x minus 1/5 of sine x, and if we plugged it into the left side, it would have produced a sine x, which means this is the solution. This is one solution to the given differential equation. What was, so you're going to see yp particular. So this is the solution, particular solution to y double prime minus 2y prime minus 3y equals to sine x. And if you had the time and if you're suspicious of our calculation, you can check by plugging in that particular solution to the left side to see that it is equal to sine x. That's how you would spot an error. So if during the exam you finished thoroughly and you still have maybe had like 20 minutes, then the way you would check your answer is by directly plugging in your answer to see if it does produce the right. So that's one particular solution. Now let's find a complementary solution, which is the complementary equation is you have y double prime minus 2y prime minus 3y equal to 0, which has the characteristic equation r squared minus 2r minus 3 equal to 0. R minus 3, r plus 1 equal to 0, so you get r equals to 3 and negative 1, and that gives you the solution. What's the solution in this case? E to the 3x, right? And then e to the negative x. 3 and negative 1, quoted from the solution of the characteristic equation. You put C1, C2. And this is what we call the complementary solution. Okay. What kind of property does this have? It has the property that if you plug this into the left side, what would it produce after calculating all that?
0.
It will produce 0. Okay? Therefore, here's what we know. If we just take y general as y complementary plus y particular, which is C1 e to the 3x plus C2 e to the negative x. That's the complementary one. And the one that we found as the particular one was 1/10 cosine x minus 1/5 of sine x. If we take this sum and plug into the left side, what would this produce? Well, first, this one will become what? It will become 0 because it's the solution of the homogeneous one. What would this become if you plug into the left side? It will become sine x. Therefore, if you put the entire thing into the left side, you're going to get sine x, meaning that this entire thing is a solution regardless of the value of C1 and C2. Now, why is it important to have C1 and C2? Because when we are given this, so we're saying that this is the general solution of y double prime minus 2y prime minus 3y equals to sine of x. See, it's important to have two free parameters as a solution to this differential equation, because you could also be asked the same equation with two given initial conditions. Here I didn't give it to you, but you may be given these initial conditions, the value of y is 0 and y prime is 0. No matter what I give to you, the theorem proved by mathematicians say that if you provide these two initial conditions with this differential equation, there should be one unique solution satisfying it. Okay? And indeed, in order to make that work, you do need these C1 and C2, because without it, you can't make it work. But with it, no matter what kind of value I put, let's say I put 3 and negative 2 or whatever, then you can plug this into the left side and make it work, right? You can solve for C1 and C2, and you have the solution, right? So that's why you really require both of them to be the general solution, okay? Okay, so that was the review of what we call the method of undetermined coefficients. So let me write down the title after doing all this work. So this method is called the method of undetermined coefficients. And the name of the method kind of explains itself, right? If you look at what we did, why is it called method of undetermined coefficients? Because first we kind of made a guess what kind of functions would create the right-hand side. But then because it was hard to nail down the correct coefficients for those functions, we made them undetermined. We used A and B, capital A and capital B, which was to be determined later. Okay? That's the beauty of this method. Okay? You're kind of making guesses, but not entirely, because you don't want to do the calculation over and over. You just put the coefficients very generic, plug it in, and then make the differential equation itself determine the coefficients, right? So that's called the method of undetermined coefficients.